hydroelectric power plant, 100 meters cubed per second of water flows from an elevation of 120 meters to a turbine, where electric power is generated. The total irreversible head loss in this piping system from point 1 to point 2, excluding the turbine unit, is determined to be 35 meters. If the overall efficiency of the turbine generator is 80%, estimate the electric power output. So in order to start this problem, we have to first write down our given values that the problem gives us. So we start with our volumetric flow rate that is given to us, which is 100 meters cubed per second. And we also have the height, which can also be called G1, which is 120 meters. And our head loss, which is 35 meters. And our efficiency of the turbine, that is 80%. So in order to start this problem, we have to convert the volumetric flow rate into mass flow rate. And in order to do that, we know that 1 meter cubed equals 1,000 kilograms. So, and in order to find mass flow rate, we have the equation density times volumetric flow rate, which equals, so it's 1,000 kilograms per 1 meter cubed, which is the density of water, times the volumetric flow rate that we have, which is 100 meters cubed per second, which gives us 10 to the 5 kilograms per second.
We have three different equations for Bernoulli, and since we were looking for the head losses, we're going to use the first one. We have difference, which is for pressure and for energy. So let's use the first one. So we will have pressure 1 over rho g plus velocity squared over 2g plus z1 plus the head of the pump plus pressure 2 over rho g plus velocity 2 squared over 2g plus z2 plus head losses plus head of the turbine. We can cancel the pressures out because we have the same pressure at point 1 and at point 2. The velocities also can cancel out because the velocity is constant. C1 equals 120 meters. And we don't have any head because we don't have any pumps. So this is equals to Z2. And C2 we know it's 0 because the datum is going to be right here. And the head loss it's given, which is 35 meters plus the head of the turbine. It gives us 85 meters. Now with this information we can find our power in the turbine. So we know the equation that equation. So first we're gonna prove with the units. We know that the mass flow rate is kilograms per second times gravity, which is meters per second squared, times the head loss, which is measured in meters. We know that the work per time it's kilograms meter squared over second cubed. And if we multiply this, it's going to be kilograms meters squared over seconds cubed, which is the same. So now we can look for the power, which is going to be the mass flow rate, which is equals to 10 to the 5 kilograms per second times the gravity, which is 9.81 meters per second squared, times the head loss in the turbine, which is 85 meters.
Yep.
And the result, it's going to be 83,400,000 watts, which is equals to 83,400 kilowatts.
Now in order to find, we have to find the total power electric, and in order to find that, we're going to use the equation power electric, which equals our work total times our efficiency, which is 83,000 kilowatts times the 80%, which is 0.8 out of 100, which gives us 66,700 kilowatts. That's how efficient our turbine is in this problem.